Joyce Parker is an assistant professor of geological sciences and teacher education at Michigan State University. She spent a number of years conducting research in how students understand basic scientific principles and the implications for teaching. And more recently, she's been a collaborator with the Great Lakes Bioenergy Research Center, which is based at University of Wisconsin-Madison and with Michigan State as its major partner. And she's been conducting research into how students understand basic concepts related to climate change and how they use that reasoning to be able to understand the options for mitigating the effects of climate change. So, with that, I'll turn it over to Joyce and welcome her for her presentation today.
Thank you, Scott. I'm happy to be here today and share some new results with you all. But I want to emphasize that these are not solely my results. This is actually the result of a large collaboration at Michigan State University, headed by Charles or Andy Anderson. We have a large group of people working on an R&D environmental literacy project called Carbon Time that's NSF funded. And these two grad students, May and Craig, have been analyzing a lot of the data I'm going to show you today, along with Beth Covet, who was a postdoc in the project, who's now at University of Montana. And the other two folks who've really helped out a lot are John Greenler and Leith Nye. They're at University of Wisconsin in their role in GLBRC's education and outreach. We've worked with one other group, and that's the Center for Integrated Studies in General Science at MSU. That is the group or the unit here at MSU that teaches courses for non-science majors. And they teach many of their courses, at least touch on climate change and energy use. And we see their students as sort of a stand-in for the educated public, so we do a lot of work with them. So I thought the best way to start would be to tell you our research questions. What is it we're trying to figure out? Well, the first thing is, what knowledge and reasoning skills do people need in order to be environmentally literate when it comes to climate change? In other words, what do you need to know, and how do you need to be able to reason to understand the ongoing issue of climate change? So where's a reasonable place to place the bar for environmental literacy related to climate change? And then once we place the bar, the next question is, how literate are high school and undergraduate students in this regard? How close to the bar do they come? And finally, once we understand how students are or aren't reasoning about climate change, what are the implications for teaching? So I'm going to spend the bulk of my time on that first question because that's where we've done the most research. But towards the end, I will answer the other two questions as best we can at this point. Those are still ongoing pieces of work. So what knowledge and reasoning skills related to climate change should the public have? Well, climate change and energy use are different from some other topics that we teach in that they're ongoing issues. So there's a stream of new information coming in, new data, and changes in human activity affect the system. So there isn't a fixed package of knowledge that we could teach all students and prepare them to deal with these issues. Instead of a fixed knowledge, we need to emphasize reasoning skills or to use Bransford's phrase, we need to prepare students for future learning. So each time this issue comes up in the future, people will have to learn about new data or new factors and make new decisions. And so it's that kind of learning that we have to prepare them for. Well, that sounds good, but what does that involve? We think it involves, those reasoning skills involve these three aspects. Being able to interpret data, using a model of how carbon cycles to explain events, and predicting the effects of changes in human activities on the system. So we're just going to dive in, and I'm going to talk to you about a question that's revealed a lot to us about how students think about carbon in the atmosphere and global climate change. When we study students' thinking, we use two kinds of questions. We do interviews and we use written assessment items. We do the interviews in the beginning to sort of chart the territory. Interviews are really useful because when somebody says something we don't understand or is vague or we can't follow their reasoning, we can ask a follow-up question and push a little deeper. But of course, interviews are very time-consuming, both to do and to analyze. So once we sort of have a sense of the territory, we move to written assessment items where we can get larger ends. We can ask a lot more people. So I'm going to talk to you first about interviews. The first set of interviews we did were with undergraduate non-science majors. And as I said earlier, we see these as a stand-in for the educated public. We do use the same interview protocol with second-year medical students. And our thinking here was medical students probably don't have a lot of direct training in climate change or atmospheric systems or anything like that, but they do have training in scientific reasoning, and therefore they might be more articulate interview subjects, and indeed that's turning out to be the case. So we interviewed 15 of the undergraduates and medical students, but we've also used written assessments with the undergraduates who are non-science majors, but then another group that we're really interested in. These are undergraduates who are science majors and who are preparing to teach high school. And we care about this group because, of course, they are part of the system that educates the public. And just recently, we've been moving down the age ladder to see how high school students think about these questions. So let me now show you the questions that we ask. We give students this diagram of the carbon cycle, and our basic goal is to see if they can use their understanding of how and why carbon moves in and out of the atmosphere to predict the effects of changes in human activities. So we give them this particular diagram not because it's a particularly good one, but because it's a commonly used one. It appears in many public articles. It comes from NOAA, so it pops up in a lot of places. And you can see it's fairly complex. It shows the basic carbon pools, the ocean, vegetation, and soil, the atmosphere, and they're not drawn to scale, but they do have numbers on them that indicate the size of the pool, and those numbers are in gigatons of carbon. And then there are a whole bunch of arrows that show how carbon moves between the pools, and those are labeled with the flux rates in gigatons of carbon per year. So, as I said, nothing here is drawn to scale. Neither the pool size nor the width of the arrows means anything. But it is a fairly effective diagram in that because it's pictorial, students understand fairly quickly what it means. So we give them that diagram in conjunction with this question. We show them this graph, which shows the levels of atmospheric CO2 in parts per million, starting in about 1956 and going up to the present. The end of the solid line is the present. And then in an interview, we ask them if the world were suddenly and miraculously able to cut its use of fossil fuels in half tomorrow, what would be the effect on the level of atmospheric CO2? In an interview, we let students draw out their prediction wherever they think is appropriate. In the written form, we give them these choices, A, B, C, D, E, have them circle one and explain why they chose that answer. So we give them this question before we've shown them this diagram. We get their thinking, we show them the diagram, and then we ask the question again. So what we're trying to do is see if they can use that diagram, that model, to improve their prediction about what will happen. So what's the ideal response here? Well, before they see the diagram, we hope that they're going to answer either B or C, and they're going to give reasoning rather something like this. So this is the response of a medical student who chose a graph, or drew, actually, this is an interview. He drew essentially line B. So we're still using them, meaning fossil fuels. So I would say we would still expect it to increase, but at a much slower rate. Yeah, so we're still using fossil fuels, still contributing to carbon emissions in the environment, but if we are using less, and half of that, and at that point he points, we should expect to see slower increases in CO2 of the environment. So this person is making a correct connection between the slope of the CO2 line and the flux rate from fossil fuel use. Here's another med student who chose graph C. She says, so depending on how much carbon dioxide we're putting into the atmosphere versus how much is being taken out of the atmosphere, we suddenly start putting half as much into the atmosphere. Depending on how much we're taking out, it would either be like not as steep a slope, they're sort of about equal, or we're taking a lot more carbon dioxide out of the atmosphere, and then we're putting in, then it would be a steeper slope. And she means steeper slope down is what she's drawing. So you could see line C goes up and then down. So she's talking about how steep the downward part of that trajectory is. She's gone a step further than the previous student in that she's talking about influxes and outputs. She realizes that the slope of this line is determined by the balance between those two. But both students sort of represent the best we can hope for before the students see the diagram. Now here is the same student, this second student's response after she sees the diagram. She says, I guess if we look at this now and we think that instead of 6.3, and here she's looking at this, the flux rate of fossil fuel combustion, and or around 6, we're looking at 3. So she's saying we cut that flux in half. I think the net change would be about almost 0. So I don't know that it would actually decrease. Maybe it would just stay the same. So she's realized that the net flux over here between vegetation in the atmosphere and ocean in the atmosphere is about 3 gigatons per year out of the atmosphere. If we cut fossil fuel use in half, it would be about 3 gigatons into the atmosphere per year. So the inputs and the outputs would balance. That's the most sophisticated kind of reasoning that we can expect, we think, in this with this question. But very few students get there. So what are other students thinking? Well, some students choose A. And when you look at their reasoning, you can see that they're not thinking in terms of pools and fluxes. They're thinking about factors that are present or tipping points. So here's an example of somebody who's thinking of a tipping point. Because I think we've reached a point where we've done too much damage to Earth, personally, and I don't think we can come back from that. So this person is imagining once you do a certain amount of damage, whatever damage is, this trajectory of CO2 is fixed and it's not going to change. Another sort of related kind of thinking is if there are other bad factors still around, that trajectory of CO2 is not going to change. And here's somebody who thinks like that. We still create CO2 when we respire, so I do not believe levels would go down, especially considering our growing population. So students who reason this way, they mention that we're still using fossil fuels, they may mention deforestation, they often mention growing population. All those are bad things, and therefore the bad trajectory will still happen. There are students who choose D and E who are thinking in similar ways, only they're looking at good factors and therefore good trajectories. So here's an example of that. Because the air will be cleaner and plants will be taking in more CO2. This person chose graph D. So all of these students, their thinking goes something like this. We do something good, we cut our fossil fuel use in half, therefore we'll get a good trajectory for the CO2 levels. And there really isn't a mechanism in their thinking. They don't have an explanation for why cutting fossil fuel use in half would lead to cleaner air. It just would. And that's fairly typical in kind of response in a whole lot of different questions we ask. Good things lead to other good things, bad things lead to other bad things. Here's another example of somebody who chose D. Fossil fuels pollute our air. Well, so what they're saying is fossil fuels are bad, we cut down on their use, good things happen. And sometimes they sort of infer some kind of inertia in the system. In time, CO2 levels would decrease, but it would not be an immediate decrease. So in some of the cases, they'll draw this same fairly steep downward trend as shown here in D&E, but first they'll put a big hump in it because there's some sort of inertia in the system that keeps the CO2 level increasing, and then something else takes over and it decreases. So we haven't done enough large-scale studies yet for me to tell you how many students fall in this category, but I can tell you that there's a bigger category of students who choose D&E but for a different reason. And they're choosing D&E, they're trying to think about pools and fluxes, but they are having a lot of trouble. They conflate the flux, that is the inputs and outputs, with the pool size. So let me show you an example of that. Because fossil fuels help to produce CO2, so if we cut it in half, it would decrease. Now there are a lot of "its" in that statement, and I put that in there because that's fairly typical, and it may be that that's part of the problem, that students, because their language is not precise, their thinking is not very precise. I don't know which is cause and which is effect, but those two often go together. But anyway, we get a whole lot of students who say, if you cut this flux in half, the pool size will go down. And sometimes that leads to inaccurate mathematical approaches like this. I guess it would definitely be down here, like around 200, because we're at 400 right now. So if we cut it in half, so she's saying we go from 400 to 200 if we cut the flux in half. As I said, that's probably the largest group of students, at least before they see the diagram. And that is worrisome because these students are seeing the problem as easier to solve than it really is. They're thinking that any downturn in the flux will lead to a downturn in the pool size, whereas we would have to cut our fossil fuel use almost in half in order to just balance the influxes with the outputs. So this is very problematic. So let me try to put all these different types of answers in some sort of order for you. The least sophisticated thinkers are those who aren't thinking pools and fluxes. They're thinking about good factors or bad factors. Then there are these folks we just talked about who are conflating pool size and fluxes. Among undergraduates, that's probably the biggest group. Then there are those students that I showed answers represented by the med students who are thinking about pools and fluxes in accurate ways, but perhaps limited ways. And limited in the sense that they don't think about all the fluxes at once, but at least they understand that their pool size and flux are not the same. And finally, at the top of the scale, we have those students who can think accurately and quantitatively about pools and fluxes. So you can see there's quite a big gap between these lower levels and this upper level. And some of the other questions that we typically ask help us understand that gap a bit. So, as I said earlier, students are probably in the future going to see new information, often in the form of graphs. So one question is, how do they interpret graphs? Well, one problem is that the graphs and the techniques for gathering and processing data that are shown in graphs that relate to energy use and climate change are less familiar to students than investigations they're used to having done in, say, high school. Things are on a different scale, and they often involve complex averaging. So let's look at this graph here. The first graph. This is the CO2 concentration in the atmosphere taken from Mauna Loa in Hawaii, and each dot represents a monthly average. Monthly average is not a kind of data that students have experience with. They may be able to think about some reasonable ways to collect monthly data, but that's not something they have direct experience with. Then think about, let's say, a graph of average global temperature. That has a very complex averaging going on because you have to average over a time, a year, and over the whole globe. And that really is hard for students to understand. And the other issue here is we're talking about data that we use to represent both local and global systems. So, for example, this CO2 graph, the data are taken at one location, Mauna Loa in Hawaii, but they're used to represent what's going on all over the northern hemisphere because the atmosphere is a continuous, fairly well mixed entity. But students don't think that way. They think much more locally. And so that's confusing to them. The other problem is that many of these graphs have both short-term variability and long-term trends. So in the CO2 graph, the short-term variability is very regular and it's an indication of a trend in the seasonal activity of plants in the northern hemisphere. So between May, which is when the peaks are, and October, which is when the troughs are, plants in the northern hemisphere are more active. They pull in CO2 and the CO2 levels actually go down. And then between October and May, they go back up again as the plants become dormant. But students try to explain that using only single cause, and I'll show you in a minute why that's difficult for them. But that kind of variability is different from the variability in this graph where you see the Arctic sea ice extent. Here the variability is because it's a stochastic, sort of randomly changing system. And students may see the randomness here as the pattern. So if you ask them to extend this graph, make a prediction about how Arctic sea ice is changing, they may say, well, between the last 2 points, the graph went down, so the next time, for the next year, the graph is going to go up. So they see the variability as the trend, and they don't have the statistical skills to see if there is whether or not there's a real downward trend in that data, in those data. So having more than one trend or variability in a graph is another thing that's hard for students. Once they've determined trends in data, we want students to be able to explain them. So again, the CO2 graph is different for them than the Arctic sea ice graph. in general, we find that the number of successful students is roughly inversely proportional to the complexity of what we're asking them to explain. So they're relatively successful at cause and effect chains. So if you look at the Arctic sea ice graph, they can explain that by saying global temperatures are going up, therefore Arctic sea ice is going down. That's sort of direct cause and effect argument they can make. So they reason, well, maybe in the summer people use less, they drive less, or they use less fuel to heat their homes. So they stick to one cause, and therefore they can't handle complex relationships like what's shown here. And the other problem is they're not aware of when their explanation doesn't fit all of the data. Right. Let me go back to that. Let me find a picture of that. That is a great question, and we have tried it. Oh, I have to go way back, I guess. We have tried it both ways. And I'll show you the actual results for this in a little bit. But when we just give them the diagram, no discussion at all, we still see some improvement in their answers. When we give them a chance to use a hands-on version of the model of the carbon cycle, then we get even greater improvement in their answers. So that's a great question. Did you want to ask some more questions? Yeah, so some of our other work has gotten at that. Um, a lot of students come to the university being able to say that CO2 in the atmosphere causes warming, but they don't understand the mechanism. So a lot of students bring ozone into the picture. We think that that's something that's maybe commonly mistaught in high school. So they say CO2 damages the ozone, which leads to global climate change. Obviously, they're mixing up stories there. One thing that the good side of that is we're finding that students don't necessarily have to understand the mechanism of how CO2 leads to climate change to be able to do this sort of pool and flux reasoning. So I guess that's the good news. And I'll show you some data in a little bit about how students do get confused about these small parts per million changes, and they get sucked into some sort of denier arguments, and where they go something like this: 6 gigatons per year into the atmosphere from fossil fuels is really small compared to what's going into the atmosphere from the oceans and vegetation, and therefore we don't have to worry about it. They often think we don't have to worry about small, like 0.2 degrees increases in global temperature. It is true that all those small numbers, um, they don't think in terms of percent change, and they don't think of the size of the consequences. So let me get back to where we were. This is a question that I know you folks who teach about energy use might be interested in. Because I work at GLBRC, we're interested in how students understand biofuels. So we ask this question. We give students this diagram, and then we say, would substituting biofuels for some petroleum-based fuels be of benefit? And most of the students abandon biofuels as soon as they find out that biofuels produce CO2 when burned. So that's usually the first thing they ask when you say yes, just like petroleum-based fuels, when you burn it, you get CO2. They're not interested. Even those students who realize that biofuels crops sequester CO2, pulling it out of the atmosphere, and then release it again when they're burned. They don't think about net fluxes, which was, remember, on that scale of 1 to 4, that was the top level of thinking. Because they don't get to a net flux, they don't see the benefits of biofuels. In fact, we have yet to find a single person who answers this question and thinking about the net flux. So that is when it comes to multiple fluxes and comparing them, students really do not have a mechanism for doing that. So for us at GLBRC, that's our next big task. And maybe to sort of sum up this part about how students think about it, we're thinking of this predicting outcomes of changes in human activity as the pinnacle, the top kind of reasoning that we want from students. And it combines some unique features of its own, but it also requires they interpret data and graphs and explain events. So it's a really complex kind of reasoning that we're going after. That said, how well do we do? Well, in the only large-scale study that we've analyzed so far, we gave this question to 100 incoming freshmen without the carbon cycle diagram, and only 12% were able to give a reasonable response. That's the glass half empty answer. Here's the glass half full answer. We think this kind of reasoning is teachable. And here's why. And this refers back to Pat's question. Both with seniors, the seniors who are becoming science teachers, and freshmen, when they got to work with a hands-on carbon cycle model, their response to the half fossil fuel question improved dramatically. More recently, we've gotten data from high school students who were simply asked the half fossil fuel question, given the diagram without discussion, and asked the question again. And even they showed improvements in their answers. Now, some of them showed improvements. A smaller number actually got confused by the diagram. And so that begs the question, How are students using the model? Well, the way the model seems to help students is if they're not already thinking in terms of pools and fluxes, sometimes it moves them towards that kind of thinking. If they are thinking about pools and fluxes, but maybe only the flux from fossil fuels, the diagram gets them to see the bigger picture and think about multiple fluxes. Those that are thinking about multiple fluxes use the diagram to get to that quantitative level of sort of peak reasoning that we want. And then some students have an aha when they see that all of the fluxes are paired except for the one from fossil fuels. So that is a big aha for some students. Students are confused by the diagram just because it's so complex. They worry about should they be paying attention to these natural fluxes, which are shown in blue, or the anthropogenic fluxes, which are shown in red. And as John asked, are they confused about all these different relative sizes? And indeed they are, especially the younger students. So those high school students who were confused when they looked at this diagram, they noticed, wow, look at all this carbon in the ocean. Maybe I should just be looking at the fluxes in and out of the ocean. So these relative sizes, pool size, flux rates, a whole lot of both, is very confusing for students. But as we said, when they work with the hands-on model, we think they can get the hang of this kind of reasoning. So that brings me to my last point. Given what we know about how students think, what are the implications for teaching? Well, first we said that this kind of reasoning is complex and it has these three components: interpreting graphs of large-scale data sets, explaining carbon transforming events, and then predicting outcomes of changes in human activity. Students need to practice all of those separately and then all together. And so lots of scenarios and problems about what if we change this, what if we change that, would be, we think, are important. The other thing is we found that working with the dynamic pool and flux models was important. And so let me show you what we actually did with that. So with those seniors who were becoming teachers, one of the things we did was we played with water in reservoirs. We set up 3 linked reservoirs. Each one has a fat tube and a skinny tube coming out of it, so we could do all kinds of influxes and outfluxes, and then we could look at the effect on that middle pool. So if you have a small influx and a large outflux, what happens? How do you balance, keep the pool size constant, but still have water running through that? That idea of a dynamic equilibrium is hard for students. And on top of that, we use this GLBRC activity that you can see here with the Petri dishes and the checkers, where the students make a scale model, both of the pool size and the flux rates. And those are the models that we used that helped students make the biggest changes in their responses about having the fossil fuel use. But we think that even that is probably enough. That's good to help students develop an intuitive sense of what's going on with pools and fluxes, but they probably should play through a lot of scenarios. And these are not the best ways to do that. We think that we're going to need to develop some computer simulations to do that, and so that's in the works. So that's all of the data I'm going to show you. There are a whole lot of questions that we still want to answer. Things like, is this truly a learning progression? Remember I showed you, I lined up the levels of thinking 1 to 4. When students learn this, are they really going to progress through that, or are they going to jump around thinking in different ways? How successful are the curricula that we've already developed in moving students towards this more sophisticated reasoning? How well do these reasoning skills inoculate students against climate denier arguments? We find, I guess the good news there is that we're just tiptoeing into this right now, but it feels like we don't find very many deniers among our students, and when they know a denier argument when they hear it, but they really can't debunk it. So they just say, well, I don't think that's right, but they don't have a mechanism or the reasoning skills to figure out why those arguments aren't right. We're curious about how these reasoning skills relate to other reasoning skills. That is, can we teach reasoning in some other context and then expect students to transfer it to the situation of climate change? And finally, how do different representations affect students' ability to interpret data? A lot of the climate change data is represented in color graphs and things like that. Are those easier than numeric graphs? Those are questions we're working on. And so that's the end of my talk. I want to thank our funders. This is very person-intensive research, and so NSF has funded and the Department of Energy have funded this research.